So far, we looked at the observations in visible light, which also corresponds to the redshifted rest frame ultraviolet light in galaxies. In other words, what you just see directly in stellar surfaces. However, we do know that galaxies contain dust, and likely they did so from very early on. The dust absorbs ultraviolet and visible radiation and re-emits it in far infrared or submillimeter. Thus, there has to be an obscured star formation component involved in galaxy evolution. And indeed, as we acquired ability to observe deep universe on these wavelengths, it was discovered that there are new sources appearing on the sky that were simply not visible at all in visual light. Here we see a composite in the upper left, visible light image from Hubble and the mid-infrared image from the Spitzer Space Telescope. As you can see in the upper right, there isn't a trace of that red source. In the lower left, you can see it just beginning to show up as you go to near infrared, and on the lower right, its pure mid-infrared imaging source is very obvious. So the sky would look different on these wavelengths, and there could well be a previously unaccounted population of sources. And this is indeed the case. The first observations that uncovered such a population of sources were done at James Clerk Maxwell Telescope in Hawaii. It is a sub-millimeter telescope. It was equipped with a bolometer array measuring sub-millimeter radiation from sources in the sky. These are very difficult observations to make. This is why it took so long. And they looked at a couple of the deep fields, the Hubble Deep Field and another one called Lockman Hole, and found that there are sources there. Faint sources whose nature at that time was unknown, but were almost surely obscured star-forming galaxies far away. The reason why they look so blobby is the poor resolution of these telescopes. You may know that the angular resolution of telescope is proportional to its diameter divided by the wavelength. So for optical, this is a very high number. There are many wavelengths of photons stretched over, say, mirror of the Keck telescope. Not so in radio or submillimeter. There you have very low resolution. Nowadays, we have new interferometers like ALMA in Chile that will actually produce optical-like resolution, these wavelengths. But back then, this wasn't the case. Now, here is a really nearby example of what we might expect. This is the galaxy M82, which is a nearby starburst galaxy. And the picture shown here combines regular visible light, and the purple is ionized hydrogen emission. What we see here is an intensely star-forming disk galaxy obscured in the middle, but the supernovae exploding push the gas out. They drive a galactic wind, expelling it into intergalactic space. Now, if we take a broadband spectrum of M82, we see that there are two bumps. There is one in the optical, which corresponds to sort of quasi-black body sum of all stellar photospheres, and a bigger one in far infrared, which is thermal emission from dust that was heated up by these young stars. In this particular galaxy, there is actually more energy emerging in the form of submillimeter of far infrared radiation than visible light. But on average, in this part of the universe, there is roughly equal amount of obscured and unobscured star formation. The same turns out to be true at higher redshifts. You may recall the concept of K corrections, which means that as you observe in some stationary instrument on planet Earth, you're looking at different parts of the rest frame spectrum for sources of different redshifts. Now, by and large, for galaxies, this makes them dimmer because galaxy spectra tend to be redder, more energy in the red part of the spectrum. It turns out that for submillimeter sources, it's exactly the opposite. You're redshifting into the Planck curve, you're climbing from the mean side. And so even though sources get further away and therefore should be dimmer, you're sampling a brighter part of their intrinsic spectrum. And so some of those K corrections actually become negative. The upshot is that for many of these sources, the apparent brightness almost does not change with redshift. And therefore, if you can reach that flux level, you can see very far away. This is what scuba sources turn out to be. Which also means that we can do fairly deep source counts in these wavelengths, and here are some examples of it. They can be used then to constrain directly the contribution of these sources to the overall star formation history in the universe, and say something about their evolution. There is one difficulty, however. The poor angular resolution of these sub-millimeter observations means that optical counterparts, which we need in order to measure the redshifts, are hard to guess. In some cases, there is an obvious counterpart, but in many cases, there are many faint galaxies inside this arrow circle of a sub-millimeter source, and it's not clear which one, if any, of them is the actual counterpart. So it took a while to get redshifts measured for these objects. The trick that was used is that radio measurements can detect some of them, and radio measurements have precision that is perfectly good to match to optical observations. Then the spectra were taken of those, and in fact may turn out to be strong emission line sources, where the line emission could be powered by star formation or possibly by an active nucleus in those galaxies. Possibly a little bit of both is happening. And the predictions from fitting the source counts were that many of these sources would be around redshifts 2 or 3, and that exactly turned out to be the case. So now that we've seen how we can detect both obscured and unobscured component of evolving galaxies, we'll look into the overall star formation history of the universe.